So okay, so let us not go into the proof of this because I want to get to some applications, right? And okay, so before we go into some concrete applications, let me draw the connection with the eigenvalues. Okay, so as we saw that singular value decomposition is defined for all m by n matrices. Okay, eigenvalue decomposition was not. However, we can draw a connection between eigenvalues and singular values, and for that, let us try to write A transpose A in terms of the singular values. So what can I write A transpose A to be? If you write A as U sigma V transpose, so A transpose A is U sigma V transpose U sigma. Correct? I haven't done anything. I just replaced A as U sigma V transpose. So what does this come out to be? U transpose? U transpose. Not U transpose. Sigma transpose? Is there any necessity of writing a transpose here? Sigma is a diagonal matrix. So what do we know about U? Orthonormal matrix, U is an orthonormal matrix, and therefore this is V sigma square V transpose because this is identity. And what would A transpose be? U transpose. Okay. Now look at these two matrices, A transpose and A transpose A. If you look at these two matrices, if you look at A transpose times let's say V1, what is this? V1 is the first column of V. What is this? A transpose V1. I mean, from this decomposition that we have written, you should be able to say immediately. If I multiply this by V1, so first I multiply V transpose times V1. Well, V transpose times V1 is a vector. And what is that vector? So V1, so V transpose is V1 transpose VR transpose times V1. V1 transpose V1 is 1. V1 transpose any other Vi is 0. So therefore, this gives you 1, 0, 0, 0, 0, 0. That multiplied with sigma square gives you sigma 1 square times 1, 0, 0, 0, 0. That multiplied with V gives you sigma 1 square V1. What does that look like? This starts looking like eigenvectors and eigenvalues, right? That you multiply this matrix A transpose A with a vector, you get back a scaled version of that vector, right? In fact, this is exactly the eigenvector decomposition of the matrix A transpose A, and this is exactly the eigenvector decomposition of the matrix A transpose. Okay, so while the matrix A might not have eigenvector decomposition because it's not a square matrix. If you look at the matrix A transpose A and A transpose, you can also define the singular vectors in terms of the eigenvectors of the matrix A transpose A or A transpose. Okay, and that is important. Why? Because the power iteration that I mentioned, that really works on basically the algorithm to find out the singular vectors, that really works by actually constructing these matrices A transpose A and A transpose, and then doing power iteration on them to find out their eigenvectors, which gives us the singular vectors of the matrix A. Okay. So there is also another trick question, which is maybe we'll put it in the tutorial today. Let's skip that. Okay. Okay. So here is one immediate application of SVD, right? You will see this term, principal component analysis, right? And even yesterday, I think we might have run some code that that sort of does a PCA of some images or the digits or something, right? And what we really are doing there is what we say is that we're finding out the principal components. First principal component of the data, second principal component of the data. What is really happening is nothing but SVD. It's SVD with some pre-processing on top of it. What is the pre-processing on top of it? That when we get a set of data points, let's call the data points x1 to xn. We first create the mean of the data points, right? And then we subtract off the mean from everybody. So instead of considering the original data points, we do a mean subtraction from everybody, and then we take the SVD of these, right? That's it. That's all what PCA is, right? And when we talk about the k principal components, the k principal components of the data, we are doing nothing but taking the top k singular vectors of this matrix. Of this matrix that contains the x1 minus x bar and xn minus x bar in the rows, right? If you want the, so if you want the principal, if you're putting the points in the rows, you want the right singular vectors. If you are putting the points in the columns, you want the left singular vectors. Basically, that's it. Okay. Okay. So let's. So another way in which you see in which you will see that this is being done is that the algorithm for constructing the k-PCA is nothing but taking first you're centering the data by subtracting the mean, right? And then you're creating the covariance matrix. So what is happening when you're creating the covariance matrix? You're doing A transpose A, right? And then you're taking the top k eigenvectors of A transpose A. But we already saw that the top k eigenvectors of A transpose A is really the same as the right singular vectors of the matrix A, right? So therefore, all that we are doing is this. So remember this. Any k-PCA algorithm might have fancy names. It's really just taking the singular vectors. Okay. So here is another very interesting application of the singular vector decomposition, which is actually in ranking, right? So we'll do this quickly. So suppose we have the following problem, right? Suppose we have a bunch of web pages. Okay, a bunch of web pages, and these web pages, they're all linking to each other. Okay, and suppose we have kind of we're trying to find out their rank. Okay, so and somehow we know that this linking structure, if a web page is linking to another one, that is some kind of an indication that there is that this web page is saying that the web page 1 is saying that web page good 2 is actually somewhat good, because otherwise I would not have linked to it. Okay, so one thing that we can do is obviously something known as page rank, which you guys might have seen about, but there is an alternate way of sort of formalizing this problem, right? And that is as follows, right? That we could say that there are two categories of web pages, and typically there are. It's a natural way of thinking about web pages, right? So we could say that there are these authority web pages, which are really web pages about individual topics, right? Let's say one web page about sports, one web page about politics, and so on. Then there are these hubs. Hubs are nothing but web pages that sort of curate authorities. Right? That let's say one web page comes up that says that, okay, here are nice pages on the web that are talking about sports. Here are nice pages on the web that are talking about politics. Right? You could think about Google News as one of these hub pages. That's saying that, okay, that these are the good pages about news. Right? You could think about one blog post about sports that's to be a hub page that's talking about different that is linking to different good sports pages. Okay, so suppose we say that, okay, for each web page, let's imagine that I want to give it a score, right? Which is an authority score, which is that how good. What is the amount of good information or how good it is in sort of curating an information about a particular topic. And I also want to give it a hub score, right? Which is a score that represents how good is it in collecting information about other authority pages. Okay, so there are two types of scores I want to give, instead of potentially one that is given in PageRank. Okay, so I want to define it in this following way. That intuitively, I want to say that a web page should have a good hub score if it has collected information about good authorities, right? you are a good person if you are friends with good people, right? On the other hand, good authorities are ones that are pointed to by good hubs, right? This is also natural. So, however, this is not really a definition per se yet, right? Because the definition is circular as of now. So how do I'm defining good hubs in terms of good authorities and good authorities in terms of good hubs. So what do I do? Right? So here is one way of making this concrete. That suppose I say that okay, let me define the matrix A, right, to be a matrix, to be the following matrix. That I represent all the web pages. I make 2 copies of the web pages. So these are the hub pages, and every web page might appear here. And these are the authority pages. And the same web page might appear here. Now I create the links, I represent the links across the web pages from the, if web page I is linking to web page J, I put in an edge between I and J here. I don't put in, let's not put in edges between these 2 or edges between these 2. All the edges are between the hub role of A and the authority role of J in some sense. Right? And I want to come up with these two numbers, hub score of all the pages and the authority score of all the pages. Okay? So let's see. How can I define this? Right? So then this definition that we are saying can be represented as follows. It's saying that look, if you are pointing to good hubs, right? If you're pointing to good hubs, then your authority score should be high. Which means that look at the hub pages that you're pointing to. Let's collect the total score of that, right? If that total score is high, then your authority score should be high. Which means that the vector A is proportional to A transpose times H. Because A transpose times H is really the sum of the hub scores of the pages that you're pointing to, right? Similarly, the vector H is capital A times A, which means that if you are pointing to high authority pages, then your hub score should be proportional to the sum of these authority scores, right? So then this is one way in which I could make this circular definition concrete. That can I come up, given the matrix capital A, can I come up with a vector H and a vector A, right, such that these 2 conditions are satisfied. That the vector A is proportional to A transpose times H, and the vector H is proportional to capital A times the vector small a, right? So now based on what we have seen, how would you calculate the vector A and the vector H, let's say? Any clue of how to calculate the vector and the vector H? Because I'm talking about it right after SVD, SVD has to play in this somehow. This is what you're saying. And so this starts looking like H is the right? So the way, so if I think of iterating these 2, if I think of, let's say, initializing this capital A and capital H, and keeping on iterating until I reach a stable point, where I'm going to stop is really H being the top eigenvector of A transpose, and small a being what? What would be the authority score? The top eigenvector of A transpose A. Another way of saying it is that A would be the right singular vectors of small a would be the right singular vectors of capital A, and small h would be the left singular vector, the topmost left singular vector of capital A. Okay, so that's one way of looking at it. Okay, I'll just close with this one, which is an application of recommendations, of SVD to recommendations. Okay, so recommendation systems is something that all of us are familiar with. I mean, we use Netflix, we use Flipkart, we use Amazon, and all that they're really making money in is by doing recommendations to us. Really, right? That they keep a very large inventory of products, and based on what we buy, they're doing recommendations to us, and we find these recommendations useful mostly, and that's really how they're making money. So how do we formulate this? How do we formalize this problem? Okay, so let's try to formalize this problem as follows: that suppose we are given a set of users, right, and a set of items, right, and suppose we're also given a set of preference values for some set of pairs, right. So think of these preference values either as ratings, that maybe the items are movies, and you have rated the movie after you've seen them, or these preference values could be 0, 1, saying that you have gone to Amazon, you've actually bought this item, right? So which means that you need this item in some sense. Okay, so you have this matrix of users versus items, and you are filling in these entries, some of the entries, right? Either by 0, 1, or by real numbers, or by some rating between 0 and 5, or whatever. We have some values here. Right? So now what we have is some set of values in this large matrix. Right? We have some users who are in our system, and each of them have either rated a small number of movies, or they have bought a small number of items, and we know of some set of values. The other values I don't know. So now the question about recommendation is that given this particular user, and given that I know that she has bought these 4 items, these 1, 2, 3, 4 items, what am I going to recommend? What is the next item that she is most likely to like, or most likely to buy? Okay? In some sense, what you can say is that suppose all these other entries, all these other item entries for this row are hidden, and I want to find that what is the maximum value, right, in all these hidden entries for this particular user, and I want to select that item with the maximum value, and that will be my recommendation. Yeah. Is the formulation clear? Right? So I see a number of ratings, which means that I see a number of entries in this matrix, right? And then for any particular user, I know of some value. Potentially, I know of some things that the user has rated or liked or bought, and then I want to find what is the next item with the maximum possible value. Okay? This is how I could formulate this question, right? For instance, for this, if this user has sort of seen, let's say, some of these Harry Potter movies, or some of these movies. Let's say she likes Harry Potter 3 and she's put in 5 for The Princess Bride, but I want to know, okay, how much is she going to like Lord of the Rings? Okay, so why is this? So why do I hope to solve this problem? Because she could be, I mean, this could be anything, right? But here's the point. Right? That suppose I know that one other user who's also liked Harry Potter likes this Lord of the Rings. Right? Then maybe there is some logic to the preferences. There is some structure to the preferences. Right? Then although I don't know this, right? Because I know that these two are close, right? And suppose this happens for a number of movies. And because I know that these come from a specific type of movies. Suppose I'm able to see that the same category of users, right? That a bunch of users have similar preferences for these kind of movies, right? Then maybe I could try to extrapolate, right? What this should be based on maybe what other users have done to this category of things, right? So how do I sort of make this really formal, right? One simple way of doing it is, okay, why don't you take the average rating of this Lord of the Rings and put it in here? That's one trivial thing, right? But we can do much better, right? We can do much better in some sense, that is taking the global average, right? What we are trying to say that maybe not, maybe there is some more structure to this data, and we'd like to exploit this structure. And sort of one concrete way of thinking about it as follows: that suppose movies form these tight clusters. Suppose there's action movies that are very different from sort of thriller movies, from sports movies, from fantasy movies, and suppose each user only liked a category of movies. Right? In that case, the structure is very clear. Right? In that case, I could take, each user likes one category of movies, and I could take everybody who sort of rated these fantasy movies, I would take the average of only that set of users' for this blue user U, because this blue user likes 2 fantasy movies, and I know that she belongs to the fantasy category. But things are not as black and white, right? Each user likes different category of movies. Movies can also belong to overlapping categories. So things are not as nicely clusterable. However, what we then say is that, okay, things are not nicely clusterable, but things have this low rank structure, in the sense that although we cannot classify movies exactly as belonging to one of these categories, we can maybe come up with some kind of a topical representation of a movie. And this is what we call as the low rank structure. What we are saying is that maybe one way to think about the data is that there are several hidden topics. And maybe these topics are, I don't know, fantasy, sports, thriller, courtroom drama, romance movies, and so on. Maybe they are not, right? And maybe and maybe each user, you can think of saying that, okay, this user has so much interest in category fantasy, so much interest in courtroom drama, so much interest in romance. And this movie, right, also is 80% fantasy, 20% romance. I've used up my 100%, so that's it. Okay, and then whether a user likes a particular movie depends on whether the movie category shares the user's interest, right? So one way of thinking about it is that we're thinking about this low dimensional space, right? This is kind of like the topic space, right? And we are saying that, look, both the movies and the LOTR or the Princess Bride or the Order of the Phoenix, and as well as the users, they're points in this space. So the user is a point in the space based on his or her interest preference. The movie is a point in the space based on what the movie is talking about. And whether the user likes the movie is dependent on the distance between them, right? That if the user is close to a group of movies, then of course he or she is interested in this, right? So the rating, RUI, kind of depends on the distance between this user's representation and the movie representation. Okay. Now what are we then trying to do? Now we say that, okay, now we are trying to find, now we are given some of these ratings. Now can we try to find this decomposition, right? We'll try to find the decomposition based on the ratings that we have been given. We have been given some ratings here. Based on the ratings that have been given, we'll find the decomposition. Then we'll use this decomposition to figure out the rest of the ratings. So is the question clear? This is a very, very, very generic framework, and you'll find this useful in a lot of different machine learning algorithms, right? So how is the SVD coming into the picture, right? So the SVD is coming into the picture. So here is the problem, very broadly stated, right? That we want to come up with this representation of the users and representation of the movies, right? And we are saying that we have a bunch of training pairs. These are the ratings that have been given to us, and we'll want to say that, okay, the rating of a movie kind of depends on the dot product between the user's representation and the training representation, right? And the rating that the user is actually given on UI. And I'll try to find the A and the B so as to minimize this error, right? So A will be of rank some user by K, and B will be of rank item by K, or rather K by item rather. Okay. So how can I solve this problem? Okay, let's quickly go through one way of doing it. That suppose that here is the so can I just use SVD here? Is SVD coming into the picture? Can I use SVD? So how can I use SVD? What is the rank of the matrix AB? Why am I even talking about SVD? Supposing A is user by K, B is K by item, what is the rank of the matrix AB? No, rank, not the size. Rank of the matrix AB is at most K, right? So the rank of this matrix, the rank of this matrix is at most K. So in some sense, I'm representing A by a low rank matrix, which is where SVD comes into play, right? And I'm saying that what is the low rank matrix that minimizes this error, right? Which is the Frobenius error. Now SVD immediately comes into the picture, right? If I did not have these training pairs, if I were summing over all possible UI, then what would this AB be, the best AB be? It would be exactly the matrix, the low rank representation of the matrix R, the RK. Okay, but that doesn't really work because I have the training data, because I have the only the training pairs, which is only a small number of pairs. So one way of handling it, it is as follows: that you kind of try to fill up the missing entries. You try to fill up the missing entries using let's say some average, right? You try to fill up the missing entries using some average value, then you find the SVD, right? And once you have the SVD, you again try to sort of re-estimate the averages, right? And then keep on doing this, right? So this is one way in which you can use an iterative algorithm in which you can use SVD here. You're trying to really sort of minimize the error with respect to the entries in the training matrix. But using SVD, you cannot do that because then the missing entries have to handle somehow. So try to fill in something for the missing entries, either 0 or some global average. Then do an low rank SVD, right? Then see what are the missing entries. Try to again get a better estimate of that and keep on doing this, right? This is one way of doing it. A slightly better way of doing it, but this has its issues in the sense that it's not clear that it converges and so on. A slightly better way of doing it is using something known as alternating least squares, right? In which we explicitly take this particular objective function. We might be adding some regularizations to it, and then trying to optimize this particular problem using a technique that you will get introduced to regression that Arun is going to talk about, and basically you keep on doing regression. You keep on doing this alternate least squares. So once you know an estimate of A, and finding out an estimate of B is really becomes a least square problem. You find out an estimate of B, you fix that estimate of B, finding out an estimate of A is again solving a least square problem, and then you keep on doing this. Okay, so and that's one way of solving this problem. So this is SVD with missing entries. Okay, we won't go into the details of this. Okay, so let me kind of try to wrap up. So let me talk a little bit about this because you will also see this in some of the homeworks. See, one problem when we did A equal to U sigma V transpose was that we are putting in orthogonality constraints in U and V. What that really means is that U and V will have negative entries. We'll have both positive and negative entries because orthogonality constraints naturally brings in negative entries. So one problem with that is that sometimes it becomes a little hard to interpret. So another important category of matrix factorization is when you say that, okay, I'll decompose it into two low rank matrices, right? W and X, right? But both of them have to be non-negative. Let's say that the original matrix itself is non-negative. Then I want to decompose it into the product of two low rank matrices such that this is minimized, the Frobenius sum is minimized, but both of them are non-negative. How do I solve this problem? SVD does not solve this problem, right? And currently, there is no sort of guaranteed way of solving the problem. Again, what we do are variants of alternating least squares and things like this, gradient descent and things like this. But this has been, but this is very useful. This is very useful in terms of it's known to give that it's known to give much better representations of data in many settings for images, for documents, and so on. Works much better in visualization. Here's an example with this phase reconstruction today, and the only problem is really finding out the decomposition. It takes a little more time than SVD, but not too much. Okay, so just to summarize, what we did was learn about the basic method for dimension reduction, which is singular value decomposition and its connection with principal component analysis. We talked a little bit about the generalization of SVD for the case of missing data. We talked about application of SVD in hubs and authorities and in recommendation systems. We didn't get to talk about the connection of SVD with k-means, but please feel free to look at the slides for this. Any questions? Okay, Thank you.